Hello, we will be doing experiment number 7, the reaction kinetics in redox reactions. Before I start this particular experiment to explain to you how it is to be conducted, I'm going to first go through some small amount of theory so that you get a concept idea, followed by just a general introduction using the program to see where the information is available. After that, I will stop the share in between and then open another document to show you how to set up your observation data setup. That is rather than the data setup, I would call that as the reaction setup with a template for you to follow so that you do not make any mistakes, and then continue with the lab experiment and then show you how the result and the working of the lab looks like. So now I'm going to share my screen with you. And here is the first screen that I'm going to do. It's called as the introduction screen. And here, this is basically reaction kinetics in a redox reaction. The study of kinetics for this reaction is between hydrogen peroxide and iodide ions in acidic medium. This is a two-step reaction. The first step involves the reaction between hydrogen peroxide and the iodide in presence of acidic medium to obtain or to yield iodine and water molecules. The second step is a fast step in which the iodine produced is consumed by the thiosulfate to produce the tetrathionate ion and the iodide ion. This iodide ion reacts. As it is produced, it will go back and react with the thiosulfate ion till all the thiosulfate has been used up. Once all the thiosulfate has been consumed, then a deep blue color will form, indicating the completion of the reaction due to the formation of the starch-iodine complex. This particular reaction depends upon the concentration of the reactants. Before we go further, I just want to tell you that the slow step is also considered as the rate determining step for the reaction. From the reaction relating the conversion of thiosulfate with iodine mole, we see that 2 moles of thiosulfate reacts with 1 mole of iodine, which in turn requires 1 mole of hydrogen peroxide, which will provide 2 moles of iodide. And from this, we can see that the concentration of H2O2 to the thiosulfide ion is 1:2. The rate of the reaction is based on the slow step, which can be written as R is equal to K times the concentration of H2O2 raised to X, concentration of I minus raised to Y, and concentration of H plus raised to Z. Now, in this particular rate equation, we need to define and describe all the terms that are involved so that you know what you're talking about and what they stand for. That there are in the reaction, expression stands for the rate of the reaction. K stands for the specific rate of the reaction in which the per unit time, the moles of each reactant changes. The square parenthesis indicates the molarity or the concentration in moles per liter. Then X, Y, and Z are called as the order of the reaction. The order of the reaction is the exponent to which each of the concentration of the reactants are raised to in order to satisfy the rate equation. The order of the reaction can be integer, 0, or fraction. A zero-order reaction means that the rate is independent of the concentration of this particular reactant. In the given expression, Z is equal to 0 as the reaction is independent of the acid concentration. Further, X, Y, and K are to be determined experimentally by performing a series of reactions in which half the time the concentration of one reactant is kept constant. And then the experiment is repeated by changing the reactant that was constant and keeping the other reactant now constant. Once the orders are determined for each reactant, then any one set of reactions can be used to determine the specific rate of the reaction. Now, this is an introduction, and I will stop here, and then I'm going to share my experiment table with you. That is from the chem model. So again, go to the file, open the chem model, go to file, go to new. From the list of simulation modules, select reaction kinetics in redox reactions, and you have all the introduction that I gave you is shown under the introduction with the specific equations that are there. And here we are studying the rate of change of H2O2 is directly related to K, the specific rate of the reaction, then H2O2 raised to M and I minus raised to N, where M and N are the order of the reaction and K is the specific rate of the reaction, which has to be determined experimentally. You will see in this particular experiment there is no H plus ion. That is because we already stated in the introduction that H plus, the Z for H plus is equal to 0. And so the reaction is independent of the concentration for the particular reaction. And it moves without any change because anything exponent, a number raised to 0 exponent is equal to 1. Now, again, I'm just going to temporarily stop this and open the chart showing you how to set up the experimental data setup for you. Now, please note that the example I have given, there are 1, 2, 3, 4, 5, 6, 7, 8 columns, and the headings are there. The first one is called as the set or the run. Then the second column represents the Na2S2O3 mass taken in grams, and it is dissolved in 20 mLs. Potassium iodide Ki is taken in 20 mLs, dissolved in 20 mLs. Then the amount of HCl that is taken is recorded in the next row. Water, if additional water is added, you write the volume and then the amount of H2O2 that is taken. Now, to get the total volume, you add up all the volumes in the row that you have set up. So in this way, you set up all the rows that you need, like with the numbers 1, 2, 3, 4, so that you know exactly which set contains what chemicals, and there is no confusion. Now, once that is done, now, how do I get 150? 20 plus 20 is 40. 40 plus 60 is 100 plus 50 is 150. We did not add any water over here. Now I'm going to stop this share and then go back and open the experimental sheet. Now I'm going to show you the procedure, how I'm going to do. Because if you look at it, you saw in my experimental data sheet that I had written down that I'm going to take 0.25 grams of thiosulfate, dissolve it in 20 mLs. I'm going to take 15 grams of Ki, dissolve it in 20 mLs. Then I'm going to take 60 mLs of HCl, add it to the mixture, and then I'm going to pour in the hydrogen peroxide. As soon as I finish pouring in the hydrogen peroxide, I will start the timer, and then we will wait till the color changes from clear to blue. So I'm going to show you the procedure now. Since I know the chemicals, so I'm going to select a 100 ml beaker. First, I'm going to add the chemical. The dropout menu is there. I'm going to add sodium thiosulfate, add 250 grams, 250 grams, and say okay. And then again, I'm going to go to the chemical dialog box, add 20 mLs of water, 20 mLs of water, and say okay. You will see that it slowly dissolves. While it is dissolving, I'll go to and get another beaker, 100 ml beaker. Now keep it to the right. I'm going to right click for chemicals. I'm going to add 15 grams. Please note that you will be adding the grams as asked in the experiment. So don't try to repeat my experiment. So I'm adding 15 grams because I just have to demo. Make sure that you understand the experiment and see how the color change occurs. So 20 mLs I will add, and then I will add, you can see that there is a lump of Ki. So I'm going to click on the stirrer so that it gets dissolved. Once the stirring stops, then what I'm going to do is go to the equipment, get a 600 ml beaker, keep it down, and into this, I'm going to decant my thiosulfate, return it back, decant, pour and decant the Ki by placing it above the 600 ml beaker. The two beakers are empty. Then I'm going to the right click on the 600 ml beaker, get the drop down menu, select HCl, 1 molar HCl, and I'm going to add 60 mLs and say, okay. So now I'm ready for my experiment because I have done the steps, procedure 1, 2, 3. As you can see, I've procedure 1, 2, and 3 because I've stopped it at 600 mLs of 1 mHCl. After that, it says finally add 50 mLs of 0.1 molar H2O2. So I'm going to take the drop down menu to the right so that I can see what I'm doing. Then hydrogen peroxide, we want to add 50 mLs. And this is where you have to be a little bit quick. As soon as you pour it, you start the timer and start the timer. And then once this, and please keep an eye on the solution so that as soon as it changes color, you can record it because it takes a lapse of time to turn off the timer or pause the timer. So you can see that it's going. Okay, at 27 minutes, at 27 seconds, the timer changed color. And you can see it takes me 3 seconds to quickly go get onto the timer and pause it. So under the observation, we write down the time. As per for my example, is 27 seconds. So now you can perform your experiment and do it. But please, once again, I'm reminding you, do not follow my step. I just have added extra so that I can quickly show you how the color changes and how quickly it changes. Now, once you do that, then the calculation step is there. You have to find the rate with respect to the change in H2O2, and that's is defined as the moles of H2O consumed divided by the total volume times the reaction time. Now we see that the total moles of H2O consumed is 5 times the moles of S2O3, 2 minus iron. And we know the grams of S2O3 that you have taken divided by the molar mass to get the moles of S2O3 multiplied by 5 to get the moles of H2O2, and then you have the total volume reaction time. So the moles of H2O2 divided by the total volume multiplied by the reaction time, and write the answer down. And repeat this for set 1 through 6. Then you have your table number 2, that is at the bottom below. Convert the volume in milliliters to liters, and then record the time, record the rate that you have calculated, and convert the rate to the log rate function. That is log, L-O-G, that means it is to the base 10. Once you get the log rate, then it will tell you which sets to be used. So using the first 3 sets, you plot a logarithmic graph of log of rate versus initial concentration of H2O2. And so you fill up your rate and plot the graph. The slope of this line will give you this order of the reaction with respect to H2O2. Now remember, the slope on a linear equation y is equal to mx, the value of m is the slope. And repeat that for the second part, and you'll get n. Once you get m and n, then use the expression to calculate the rate is equal to k H2O2 raised to mi raised to n to get the specific rate, because you have to divide the rate by the concentration of H2O2, with its order of reaction, I minus raised to the n order of the reaction. And once you get that, you'll get all the terms. And the generalized equation, which I showed you in the introduction now, has all the values written on it. And with that, make sure all the pictures are taken for each of the sets and record them, copy and paste them onto your Word document, then complete the results, discussion, observation, and the homework. Save that and submit it. And we stop the reaction.